to the organizers for inviting me to participate in this workshop. I hope I can be useful. Is this okay with the microphone? I hear a strange sound somehow.
Put it lower.
Not interfere with the badge. Maybe this works better. I think I can talk loud enough anyways. Is it good? All right.
Yeah, that's good.
So I hope I can be useful, but I have a confession to make, and that is I've been involved in quite a few heavy particle collision calculations. That's my topic. But none of these calculations was really done with the intent to provide data for plasma-related applications or other applications. Rather, our main interest has always been to study the physics at play, to understand the basic physics at play, and to learn about that. I'm not saying this to apologize in advance for something, and I don't want to suggest that it was a mistake to invite me, I hope not, but I'm saying this because our interests inform our decisions as to which systems we study. And so, as we are interested in this fundamental few body dynamics as it manifests itself in collisions, we are interested in heavy particle collisions that involve many active electrons, and they may or may not be of interest for applications, the particular systems we study. That's a complicated problem, and actually it's too complicated or too complex to be addressed explicitly. So what I mean by that is we don't even try to solve the full Schrödinger equation which describes the problem, which we can write down, but what we do instead is we solve models, sophisticated models, but models. And here comes the problem of the systematic error of the calculation into play, and it's very hard to assess the validity of the model, of course. And it's a sophisticated model, so that means that also within the model we have uncertainties, numerical procedures, and convergence issues. All these things come up, so that would be the statistical error on top of the systematic error. So uncertainty estimates are hard, and the truth is, in reality, normally we don't do it. What we do in practice is we compare our calculations with experimental data. That's our primary quality criterion. It also most often is the objective of our work. Typically there is experimental data around, and we set out with our calculation because we want to describe and explain this experiment. So experiment serves a twofold purpose here, and the question arises, of course, what would we do if there wasn't experimental data? Regarding uncertainty, there is still something I believe we can do, and actually there is something we are doing. And so we have something like a secondary quality criterion or uncertainty criterion. I'll talk a little bit about this today. We do a lot of testing of our models and things like that. And most of it is done behind the scene. That's a phrase I borrowed from Dima Furser's abstract. I like that. Probably all of us are doing that. And so I want to argue today that if we would do this a bit more systematically than we are doing it, and also a bit more openly, which means if we would include this in our publications, then at least we would have a good sense of the uncertainty of our calculations. It will be subjective, yes, but I think better than nothing. So here's an outline of my talk. For these problems we're interested in, we are facing a twofold challenge. First, the collision problem itself is a complicated problem. You have this many-body Schrödinger equation, and in our case, and I will describe that in 1-2 slides, what we actually have to address is a time-dependent many-electron multicenter problem, which is a tough problem. But that's not the end, because typically, or often for the collisions or the problems we're interested in, there are post-collisional processes, and if we want to get the full picture, we have to describe them somehow as well. So we have actually modeling coming up on two fronts. And then I'll try to illustrate my points with using examples from our recent research. And originally I thought I can cover 2 examples, but then I realized during the last couple of days that maybe it's a better idea to focus on just one example and provide a little bit more detail. So that's what I'm going to do. I'll focus on this example where we investigated multiple capture in a slow, highly charged ion atom collision system. This type of problem, multiple capture, in a slow, highly charged ion-atom collision is of some relevance for the problem of cometary X-ray, so it does have some application. This particular problem was motivated by an experimental study which we wanted to understand, but I think it's a prototypical problem, so that's why I'm going to talk about it. We did quite a bit of work recently on ion-molecule collisions, which of course have applications as well, but I'll only briefly touch upon this depending on how I will be doing with time. Okay, so let's get started and let's first outline the problem that we actually are facing. I said it's a twofold problem, the collision problem and the post-collision problem, so let's first talk about the collision problem to set the stage. We are interested in heavy particle collisions which are not too slow. Here what I'm talking about, the projectile velocity is of around 0.5 atomic units or higher, and this is good enough or fast enough to apply the semi-classical approximation for the collision. Is this dying? And that means that the projectile is described as a classical particle which moves on a straight line trajectory in practice. And this is an approximation which really is not an issue in these circumstances regarding uncertainty. This works extremely well, at least as long as you're interested in cross-sections which are total cross-section, not differential in the projectile deflection. But even then, there are techniques of how to deal with this pretty accurately. So that's not an issue for us here, the semi-classical approximation. Similarly, for these relatively fast collisions, we can assume that the molecule, if the target is a molecule, neither rotates or vibrates during the collision. So it's assumed to be fixed in space. And that means that in the end, we describe only the electrons as quantum particles, and the nuclei are classical particles which either move on a straight line trajectory or don't move at all. That's the framework. And that means for this framework, we have to discuss a time-dependent many-electron multi-center problem, or in more technical terms, we have to solve a time-dependent Schrödinger equation for this many-electron problem. And generically, the Hamiltonian consists of three pieces. Kinetic energy, of course, then we have interactions of the electrons with the nuclei, and they depend on time because of this classical projectile motion. And that's a multi-center Coulomb potential. You have two centers for an ion-atom collision, more centers for an ion-molecule collision, and then of course there's the electron-electron interaction. And that's basically the formulation of the collision problem. I just wanted to do this to set the stage, but this is too complicated for the problems we study to address explicitly. So we don't even try to solve this Schrödinger equation. I'll tell you a little bit later what we do when we solve models for this instead of the real deal, so to speak. Okay, so that's the collision problem. The post-collisional problem. So for this example of a slow, highly charged projectile colliding from an atom, the main process that takes place is capture in slow collisions, and my maybe somewhat poor cartoon tries to indicate that typically you have capture into highly excited states just for energetic reasons. So if you capture an electron into such a state, and if this state happens to be a p state, the electron can fall down to the ground state emitting a photon. That's a post-collisional process, and in fact for this experiment we were interested in, they measured those photons, X-ray spectra, and we wanted to understand those spectra. But in reality, this problem is far more complex because single capture into one p state is a possible process, but by far not the only possible process. Typically what you have is multiple capture because you have this strong projectile charge, and so you can capture many electrons, and typically these many electrons end up in excited states, or you form multiply excited states, and then all hell breaks loose because you have a multitude of possible de-excitation pathways, Auger processes, a radiative cascade, and somehow you have to model or describe this if you want to compare with experimental X-ray spectra, which measure only a part of this complicated post-collisional processes. If, there's something helpful about it, and this is that these post-collisional processes happen on a different time scale. So the scenario is that we first have the collisional single and multiple capture in this case, And even though the collision is relatively slow, it's still on a sub-femtosecond time scale, and that's definitely fast compared to Auger and radiative processes. And for this system, typically the Auger rates are larger than the radiative rates, so you can assume that Auger processes happen next if they are possible. You have configurations that can undergo Auger processes, and then you have radiative processes. And what we do is we deal with these three things separately. So we apply models for these three different items and somehow put it together. If the target happens to be a molecule, then the post-collisional process one typically is interested in is fragmentation. The molecule typically will break apart after electrons have been removed. And the scenario then is very similar. So the projectile comes in, it may take out an electron from this H2O molecule in my cartoon. And this, of course, happens while the projectile is still around. It can be captured again. And then eventually the molecule may break apart. So this bond may break and the proton may be emitted or whatever else may happen. And again, the fragmentation time is longer than the collision time, the ionization time. That's several femtoseconds. This is sub-femtoseconds. So again, we split the problem into two problems and combine a collision calculation for electron removal then with another model for the fragmentation. It's a similar idea. So it's a combination of models. So let me now illustrate our modeling for mostly this first example of argon-17 plus argon collision. So I'll tell you a little bit more what kind of modeling we have been doing. I said that this study was motivated by an experiment. That's the experimental paper from 2012. And I said they measured an X-ray spectrum, and that's the main result, the main plot of their paper. So you have many lines with different strength, and basically they measure the Lyman alpha series, or a part of the Lyman alpha series, for argon-16 plus, so where you have just one electron left in an excited state. One electron is in a 1s state, so this 1s NP configuration decays and goes to the ground state, so this Lyman alpha series is being measured, and these are the peaks associated with it, and we wanted to understand that. So what kind of modeling do we do in order to avoid solving the full Schrödinger equation? There are three major steps involved. The first one is that we replace the actual Hamiltonian by a sum of single particle Hamiltonians such that the Schrödinger equation separates. That's the independent electron model. That's the first thing we apply to make this problem tractable for us. Then we solve these single particle equations using a basis set expansion technique, and here the problem of convergence comes up. So we have developed a basis set technique over the years. We like to call this basis generator method or two-center basis generator method, but it's just a special method of how to expand the solutions of the single particle equations in some kind of basis, and you have to make sure that you have achieved reasonable convergence. But even then, we are not yet done, even for the collisional part, because this is just, it generates single particle solutions. We are interested in calculating cross-sections for single and multiple capture, because we assume there will be multiple capture, and actually we need shell-specific multiple capture to get a good starting point for this post-collisional calculation. What kind of Auger processes will take place and so on. So we need to apply some kind of multinomial statistics to our single particle solutions in order to get those cross-sections. So all these three steps involve inaccuracies. Okay, let's talk about them one after the other. Independent electron model. That's, of course, a big approximation, and it's somewhat uncontrolled. Sometimes it works well, sometimes it doesn't work so well, sometimes one understands that, sometimes maybe not. But there's one thing one can do which is actually useful to learn a little bit about that, and that's associated with this question. The independent electron model, in some sense, is not uniquely defined. It all depends on what kind of single particle Hamiltonian do you consider, and there are different choices. And what we do typically is we use different choices for this particular problem too, and we compare the results to get some understanding of what the range of results is that you can get from this. So in this particular problem, the Hamiltonian can be written like this. You have, of course, kinetic energy, interaction of your one electron you look at with the target nucleus and the projectile nucleus. This one depends on time because of the classical projectile trajectory. That's the big R of t. And then everything else is summarized in this potential, which you can view as an effective electron-electron potential. And how you approximate this potential, that's the question, what Hamiltonian are you using? And we consider two different ways of approximating, or modeling I should say, because there is not even a correct potential, right, of modeling this potential. And the first one is we just used a ground state potential for the argon target atom on the Hartree-Fock level. Actually, it comes from a density functional theory calculation. And we like to call this the no response approximation because it's a static potential. It doesn't change over time. So it's frozen, so to speak, to describe the situation in the initial state before the projectile is close on the Hartree-Fock level, but it never changes. And then we introduced and discussed models for time-dependent potentials, and we like to call those target response models, where we assume that this potential can be written such so that the spatial and time dependencies of this potential factorize in this way. And then the question, of course, is how do you determine this function f of t? So we have devised models for this actually some time ago, and what we did is we devised a model based on some physical reasoning, but in order to validate it, we had to test it on many systems to get some qualitative idea of how well this is doing. So I'm not going to repeat the specifics of this model. I just wanted to say this function f of t is fixed in some way based on some physical arguments, but it's definitely a model. It's just a model, as this is just a model, and maybe the best we can do is to play both models and see how different the results are. That gives us some idea. And before I show you some results, I should also talk about the second issue. Remember, whichever model we use for this potential, we solve single particle equations in a basis set expansion in our basis generator method. And the question is, what basis set do we use? That's the question of convergence. And I don't want to talk about convergence too much. I think we may hear more about this a little later. I just want to say that typically a BGM basis consists of three pieces. So for this particular problem, we include a set of bound target states. In this case, all states from the second to the fourth shell to be able to describe elastic and excitation channels. These are eigenstates of this Hartree-Fock-like argon potential. Then a set of bound projectile states, because we want to describe capture. That's the main job for this application, and we had to go up to n equal to 10 because I said capture tends to be into highly excited states. And then, and that's somehow the gist or the special thing about our basis generator method, we also include a set of pseudostates which are constructed in a specific way. They are somehow dynamically adapted to the problem, and they represent the continuum. They have overlap with the continuum. For this particular problem, we are not interested in ionization, but these states may still play a role as intermediate states, which may be populated and depopulated during the collisions. And I'll show you, at least on one slide, how important or not these states are. Okay, but I mean, in practice, we do what we all do. We start out with a basis, we check convergence by increasing the basis, testing the results, seeing the differences. All this is involved here. Okay, so this gives us single particle capture probabilities for this particular problem, and the first thing to look at is what I'd like to call net capture, shell-specific net capture, where you sum up these probabilities for one given n shell, and we sum over all electrons in the argon atom. This is why it's net capture. You don't know where the electrons come from. This is not really useful for getting data for multiple capture, but it's useful to get a first idea of how well we are doing and what this response versus no response approximations do. So here are some first results, and precisely I'm showing you this comparison of no response and target response models for the single particle Hamiltonian. So this is net capture into the nth shell 255 keV impact energy, that's the impact energy at which the experiment was conducted. That's total energy, that's approximately 0.5 atomic units projectile velocity, and that's always fixed for this application. And I show you these net capture probabilities as functions of the impact parameter, and different colors are for different shells. And the scales on the left and right panels are the same, so you can easily see they are really different, no response and response. The magnitudes are different, the general patterns are not so different, and the most prominent general pattern is that the outermost peak corresponds to the outermost shell, n equal to 10, that's the red curve here, and then when you move to smaller impact parameters, you get the peaks for n equal to 9, in green, n equal to 8, n equal to 7, and it's similarly here. So this pattern is the same, but the magnitudes of those probabilities and associated cross-sections is rather different. This is a similar plot, you can hardly see anything, for net capture, but only coming from the argon L shells. So we only look at the contributions from the argon L shell electrons, and they are of course very small. That's the same scale as before, just to illustrate that the contributions from the L shell electrons, as can be expected because they are tightly bound, is very small. So that's important to know that they don't play a big role. If you look closely, you would see that no response and response are different too, or you would see that better if I would zoom into these regions. But mainly, the message is that these electrons are not really important for this particular problem. Okay, so that's somehow still the single particle level. As I said, in order to calculate multiple capture, we have to combine these single particle solutions, and we do this in some sort of multinomial or statistical analysis, and the question is, which statistical analysis shall we apply here? And there are different options. The first we considered is something like an orbital-specific binomial analysis. So remember, argon has 18 electrons. We don't consider the two K-shell electrons because they are really just sitting there and don't do anything. So we have 16 electrons in 8 orbitals. And for each orbital, we calculate a capture probability, a total capture probability or a shell-specific probability. And then if you just combine these probabilities statistically, you can obtain something like a total probability for Q-fold capture, where Q is 1, 2, 8, or 16, whatever. That looks a bit intricate, but it's straightforward statistics on the level of the orbital-specific probabilities. You can also simplify your life and average those orbital-specific probabilities so that you only have to deal with one average single particle probability, and then you have a simple binomial formula for Q-fold capture. And you can do this for all 16 electrons, but you may find this problematic because we have seen that the L-shell electrons and the M-shell electrons behave very differently. And so if you average over them, you get something which is in between and neither represents the M-shell nor the L-shell. So another option to look at is to only consider the average for the 8 M-shell electrons and just assume that the L-shell just doesn't do anything, which is almost correct. So 3 different options, again, things to compare with each other to see how big the uncertainties associated with these different options are. This is a plot of total Q-fold capture cross-sections as a function of this Q, so it's from 1-fold to 8-fold capture. I show you 3 curves, and these 3 curves precisely come from these 3 different analyses that I just showed. And it's all within the no response approximation. I'll show you the response results a little later. So the 3 curves are relatively close together. There's a big difference here at the larger recall ion charge states, not recall ion charge states, capture charge states Q. The red triangles, that's this model where we average over all 16 electrons, these different L and M shell electrons, and that's problematic, as I said, so we have some reason to assume that this is really not true, and the uncertainty, so to speak, is more related to the difference of these two, and this is kind of out. But here in this range, they all more or less agree. Before I show you the response results as a comparison, I want to show you the basis effect at this point. So I add another 3 curves for the same 3 models. So what I've done here is I've added curves that come from a calculation where these BGM pseudostates have been omitted. So that is to say, we use the standard 2-center atomic orbital basis, with the same number of projectile and target states as before, but those pseudostates are not in the basis. And you see the uncertainty this introduces. It's relatively small, but it's visible. Cross sections tend to be a little smaller than in the BGM basis. And you have the same pattern regarding the different statistical analysis. But if we do the same with the response model, then the cross sections are really different. So that's the 3 statistical models again combined with our response Hamiltonian. Again, they are close together, interestingly, up to q equal to 8, which is different from here. And we looked into the details. That's something one can understand. I don't want to go into this, but obviously now we have a relatively large uncertainty. I mean, we would argue, and typically in our papers we do argue, that the response model is better than no response because it takes something into account in a grouped way, but it takes something into account which is completely neglected in the no response model, a dynamical change. But maybe a more conservative statement in the absence of experimental data, and there's no experimental data for these cross sections, would be to say that, well, this here maybe is something like the error bar of our calculation, because it signifies what we get if we use different models. So maybe a more conservative statement would be that this shaded area is something like the uncertainty associated with the models we play, something like our error bar for this particular cross-section. Okay, we are not yet there because that's just the capture calculation. Now we have to combine it with a model for these post-collisional processes to get in touch with the experimental data. So first come the Auger processes, and this is a big problem because if you capture up to 8 electrons, then you would have a lot of different possibilities for Auger processes, and that's a problem too complicated, at least for me, to address. Too many electrons, too many rates. So what we do is we apply a vastly simplified model. Another model comes into play here, and this is a model that was actually suggested some time ago by Hamid Ali and co-workers from K-State. And I don't want to explain it in detail, it's not necessary, but just roughly it goes like this. You only consider 2 electron Auger processes, and then instead of calculating rates, you set up a set of rules, plausible rules for Auger processes, and you assume that for a given transition, the most likely, for a given configuration, only the most likely transition will take place, and it will take place with unit probability. So instead of having individual rates, you just say this is going to happen or that is going to happen for a given configuration. One electron is being kicked out, another one falls into a deeper shell, you apply your rules again, obtain a new configuration, and you repeat all this until the configuration is stable. And here's an example on this cartoon from that Ali paper that illustrates that. So here you start with 5-fold capture according to the rules. There's an Auger process that 1 electron from the 6th shell is being kicked out. This one falls down, and it goes on, and in the end, you end up with just 1 electron in the 2nd shell. And we like to call this apparent single capture because it looks like there's only 1 electron being captured, but originally it was 5 electrons which were captured. But this would be the starting point for the radiative decay. Okay, so we combined this model with our capture calculations, and just to give you an idea what happens, here I compare again probabilities for actual single capture. That means the true single capture as it comes out of our collision calculation, and these apparent single capture contributions from the Auger cascade. This is for capture into the 10th shell, that's the outermost shell in our calculation, so it can only be actual, real single capture. There cannot be an Auger process such that an electron ends up in the 10th shell. This is 7, and now it changes if you move deeper in. This is the actual single capture, but this is a contribution from initial double capture, where you capture 2 electrons into higher shells, one is being kicked out, the other one also ends up in the 7th shell according to these rules, so it contributes to a parent single capture into the 7th shell. And if you move further in, like n equal to 3, you cannot even see the 1 electron capture, it's somewhere here, and this thing is dominated by actually contributions from 3 or 4 electron captures, which according to this OJ cascade end up into 1 electron capture in the 3rd shell. So using all this is the starting point for the last step, the radiative calculation. This is just the total cross-sections associated with these captures, the actual single capture which decreases towards lower n, and that's with all the contributions from a parent single capture added. So it gives a big contribution here. So the radiative cascade is the last step, and we can be a little bit better here because there are rates available for these radiative transitions, but our problem is that our Auger model only gives us cross-sections for having an electron left in a given n shell. We don't know anything about the L distribution. This information is lost in this Auger model. And we have to reinstate that because we need that for the radiative cascade. You need to know the L distribution. And again, we don't know, so we use 2 different models and compare to see what the sensitivity is. A statistical model where you distribute the cross-section according to the multiplicity of L, and a flat one where you just distribute it evenly. And then a radiative cascade calculation is done. Actually, we haven't done that ourselves, but our friends in Paris who did the experiment carried that out. And finally, you obtain the intensities for the transitions that have been measured from this. So we finally can compare something with the experimental data. And this is only theoretical results for intensities for these X-rays, which have been measured. I'll show you the experimental results in a minute. 4 sets of calculations, 4 different models. So what I compare here is response versus no response, and using the statistical and flat NL distributions, just to give you an idea about the range of results we obtain. Not necessary to show you which one is which. This is the range of results we obtain. The other things I mentioned before, the question which multinomial statistics, do you include the BGM states or not, are not so important on this plot. They won't change this plot. It's really response, no response, and flat or statistical distribution that define the range of results here, so to speak. You might be worried that the results depend heavily on the rules of this Auger model. So in order to test this, we changed the rules and to see how sensitive the results are. And just one example, you can end up, when you play these rules with the configuration where 2 electrons are left in very different shells, and they won't undergo an Auger process, but they will both decay radiatively. So that we would like to call a parent double capture. And so we did another set of calculations where those were included in the original set, they were excluded. And so there's another curve for this included here, and you don't really see it because it's in the middle of the pack. So I'm just saying this to illustrate that the results are not that sensitive to the specifics of this model. The experimental data are the black dots and lines, and also they are somewhere in the middle of the pack. Now which is good, in our paper we argued that our response calculation with statistical NL distribution and taking these apparent double captures into account, that should be our best calculation. And there are some reasons for arguing for that, and accidentally it's the calculation that agrees best with the data, so probably we were a bit biased by that. And like from the point of view of this meeting, I mean, there's a bit of self-criticism in what I'm saying. Maybe we should have been a bit more conservative and should have said, well, again, this is the range of results that we can obtain by changing our models in a reasonable way. And maybe we should say we expect, if there wouldn't be the experimental data, we expect the data to be somewhere in here. And they were. There's still one statement we can make, which is kind of nice. If we forget about all these multiple captures and Auger processes and only take the true single captures into account, we would obtain something which lies here, clearly outside our theoretical error bar. So we can still make the statement that multiple capture is really important for this system. So this is something I probably would have said even without knowing that the experimental data is somewhere here. Okay, I think I'm out of time, so I won't say much about the molecules, or maybe nothing at all. It's a similar game. We apply models, the independent electron model in particular, and we can apply a similar strategy to assess uncertainties. For molecules, we have some more problems. Convergence is a bit more problematic just because molecules are more complicated than atoms, and I just leave it with that and come to my conclusions and suggestions. So I wanted to illustrate that uncertainty assessment for these types of problems is difficult, and in reality, sadly, maybe we don't do that normally. What I think we can do and should do, and maybe do a bit more systematically and openly than we have been doing so far, is if we have to apply models and we have to test these models, and I think one should test them on many systems if this is possible and not just one benchmark problem, because if you have a model, some models tend to work very well for one particular problem, maybe because you have designed it for that problem, but then they fail badly for other systems. So it's really good to test it on many systems to get really some general idea. And then you have to play different variants of your models. This is what I try to illustrate. If you have a model, you can easily change it. I think that is almost always true. And if you change it in reasonable bounds, you get different results. And from that range of results you obtain, I think you get at least a somewhat subjective, but some estimate or sense of the uncertainty of your calculation. And I think this is what maybe we should do a bit more systematically than we've done so far. I thank you for your attention.